How many quantum numbers are there? How many quantum numbers? You will not be tested for it, but I'm giving you practice on it. 4. So what are those 4 quantum numbers? Can you name them? 4 quantum numbers, children? We did all these things. Yes. What are those 4 quantum numbers? Principal, magnetic, angular, and spin quantum number. Okay. Okay, Arjun. Fine. So what principal quantum number tells you in the periodic table? Principal quantum numbers. It's written here. Anil has already given the answer. The principal quantum number gives you, Ariba? Afan, principal quantum number is not, yeah, what it tells you. That's the question. The principal quantum number tells you size and energy and the period number in the periodic table, right? It tells you the shells, number of shells. If there is some element over here, some element over here, how many shells are there in this element? How many shells? Period number 4. So how many shells? 4 shells. Naisha, you change your name, please. There are 4 shells, right? Okay. So when n equals to 4, what are the permitted subshells? This is shell, right? Now we are checking for the subshells. So what are the subshells? Subshells are 0, 1, 2, 3. So when n equals to 4, L is 0. What is that subshell? Yes, this one. What is this? This is 1s. And when L equals to 1, oh, this is not 1s, 4s, sorry, this 4. 4s. When L equals to 1, then 4p, L1. When L equals to 2, 4d. And what else? When L equals to 3, 4f. But do we have 4d and 4f for this element? Do we have 4d there? No, it's vacant. It's 3d, not 4d. Do we have 4f? No. 4f will come after 4f will come after 6s. And this anomalous nature is, anomalous means they are not following the sequence. The sequence is not followed. So this anomalous is due to the shape of the, no, yeah, Aufbau principle. But remember, they have higher energies. Like 3D has higher energy than 4s. 4f has higher energy than 6s. They have higher energy. Why? Because of the shapes. Yeah, because they are more diffused. 2 numbers, 3 numbers like this. They are more away from the nucleus, right? Okay, now next question. In H subshell, how many orbitals are there? H subshell. Only 1 orbital. Arjun, 1 orbital. And how many electrons in 1 orbital? Electrons are 2. Which rule we are following here? That an orbital can have only 2 electrons, not more than 2. Pauli's exclusion principle, right? Pauli's exclusion principle. You can see my notes there. And then in the p subshell, how many orbitals are there? P subshell, children? 3. How many maximum electrons you can place? 6. But we have to follow one rule, that first we are going to place them singly with parallel spins. And then pairing starts. This is called as Hund's rule. Hund's rule. So P can have maximum 6. How many groups are there in P subshell? How many groups are there in P subshell? In P subshell, there are 6 groups because you can have 6 electrons. This is P1, this complete. P1, P1, P2, P3, this one, P4, P5, P6, and this is P6. This is P5. So there is some order is not correctly done, but that's fine. You have understood this, P1 to P6. Okay, in D subshell, how many orbitals are there in D subshell? How many orbitals? 5. How many maximum electrons you can place? 10. How many groups are there? How many groups here? Groups in this? 10. Shiler, 10. You can place 10 electrons. So you start here like this. This is D1, D2, and go up to D10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, Shiler? Because you can place 10 electrons. Number of electrons in a subshell will tell you the total number of groups, right? So here you're going to place electrons like this. Hund's rule. First, all electrons will go. Can you see how I'm making it? Please make it on your paper. Looking will not help you. Looking, watching, listening will not help you much. Draw it on the paper. Whatever I'm making on the whiteboard, try to write it on the paper. Speak, write, and type. All the things will go all together like this, right? So first, all of them will go singly. Hund's rule. Remember Hund's rule? Then pairing starts. The second electron will go anti-parallel or counterclockwise like this, or anti-clockwise or anti-clockwise like this. So one electron like this, other electron will go like this. Make it in your notebook. Okay, now F subshell. How many orbitals are there in F subshell? 7. So how many maximum electrons you can place? 14. So how many groups will be there? Groups 14. Arjun, are you writing everything in the notebook also? You made this picture in the notebook? So now all of you make this picture. Make a box. Divide into 7 parts. 1, 2, 3, 4, 5, 6, now 7. Put one electron with parallel spins like this. Hund's rule. All electrons initially will go with parallel spins. This one. How many electrons are there right now? How many children here? 7. Can I say that when F has 7 electrons, it's exactly half filled? Can I say? Exactly half filled. And exactly half filled are stable. Not as stable as fully filled, but they are stable. The reason, if you look at this electron, how many rooms are available for this electron to move around? Check this electron, children. This one, this one. This electron can move in how many rooms? 6, isn't it? It can move in all these other 6 rooms. Plenty of space for this electron to move around. This electron can also move in 6 rooms, 1 here and 5 here, right? And one is already there in which it is residing. So when we have, write down this very important rule. I will be asking you to repeat it again and again. When there is exactly half filled, the way I have made this, exactly half filled. P or D or F. I'm not talking about S. I'm talking about PDF because they have degenerate orbitals. Exactly half filled PDF subshells are stable, are stable configurations. So in comparison to fully filled, they are less stable. Remember, exactly half filled PDF subshells are stable configurations. So what is exactly half filled P? Can we make it? P has 3 orbitals. So make 1 electron here, 1 electron here, 1 electron. Yeah, P3. Exactly half filled D, make 5. Yeah, with parallel spins, Schuyler. You're getting it? Okay, give me 1 second. One student has not joined. So 5 electrons, D5, that is exactly half filled. So nature likes it. Nature is more in favor of exactly half filled than partially filled, right? And F7, which I have made here. So you make this in your notebook. You can hear me, right? So that was the story what we were doing last time. I told you exactly half filled today only. So take care. Hund's rule, Pauli's exclusion principle, exactly half filled are more stable configurations. We are learning things. And then I'm going to tell you about the Aufbau principle. We are learning new words, right? And that also we did on that day. So I'll give you a review on it before we move on. So remember, exactly half filled, or fully filled. Keep practicing it. Fully filled electron configuration. So for electron configuration, I will be writing capital uppercase E, uppercase C like this. Capital EC. Fully filled electron configurations are more stable. Write on this. More stable than, yes, Arjun, than partially filled. Oh, Naisha, he's answering. Thank you, Arjun. Partially filled orbitals. Naisha, we made it here. See this one. When you have 3 electrons, you can have maximum 6, but you have only 3, and they are 1 in each orbital. You can have maximum 10, but you have only 5, 1 in each orbital. Yeah, no problem, Naisha. Arjun, thank you very much. Children, keep helping each other, right? These small doubts, they help in learning big things. Some children, they have courage to ask their small doubts. Some children, they don't ask. So help each other and answer the questions. Yes, Shailer. Fully filled are more stable than exactly half filled, no doubt. Okay. And the most stable configurations are most stable. Noble gases, the last family, this one. No, it is just one fully filled. Like fully filled. What is fully filled of S? Yes, children, fully filled S subshell is only two. Fully filled P subshell, fully filled D subshell, fully filled F subshell. Do we have any degenerate orbitals here? So we'll not talk about exactly half filled of S, okay? So this exactly half filled is not valid on S. But do we have degenerate orbitals here? Nivriti, you are there in the class? Please answer here, Nivriti. Okay, answer. So how many degenerate orbitals are there in P? Degenerate, 3. So what is the exactly half filled? P3. How many degenerate orbitals are there in D? Degenerate in D. What is exactly half filled? D5. How many degenerate orbitals in F? So what is exactly half filled? F7. These are stable. Not as good as your inert gas configuration, inert gas, noble gases, or fully filled, but they are considered as more stable as compared to, if you see the word here I've written, partially filled orbitals. Partially filled. So fully filled and exactly half filled electron configurations are more stable than partially filled. And then we have to do the last rule, which we did last time also, that is Aufbau Principle. What's the meaning of Aufbau? Building up. It's a German word. German. It means we are building. We are building the electron configuration, the periodic table. It is based on energy order. It is the energy order. And according to this rule, electrons are filled first in low energy orbitals. They go from low energy to high energy. So in Aufbau principle, we say that electrons are filled in increasing order of energy. You can say that increasing order of energy from low to high, right? So which orbital? Now everything is visible to us. This is order of energy. This one, which is visible here. So let's start with the lowest energy. So what is the lowest energy shell? 1s, period number 1. What is the lowest energy for the second period? 2s. And then 2p. This is shell number 2. So you fill electrons in shell number 1, 2. S can have 2. Then you fill electrons in 2s2. Then 2p6. Right? No, Naisha, go in the period first. When the period is over, then go down the group. Right? Then third shell. No, there is no need of saying sorry. You are learning. 3s. After 3s, Naisha? 3p. 3p, Arjun. And how many in 3p? 6. Then period number 4. Look at the periodic table. Periodic table is telling you 4s, then 3d, then 4p. S can have 2, D can have 10, P can have 6. Then, Afan, you are there? Yeah, answering. Vivan, start answering, Vivan. You're there, Vivan? 5s, 4d, then 5s, 4d, and 5p, 2, 10, 6. 6s, period number 6. Vivan, I'm not getting answers from you. You're not responding. 6s2, then 4f14, then 5d, 10, then 6p, 6. Now let's see the next. 7s2, then 5f14, then 6d10, and then 7p6. So you can see that you don't have, this is the last shell that we have to practice, we have to memorize. Okay, this order, this is Aufbau principle. You start feeling this is the lowest energy, and these are of the, this is the highest energy. Yes, by heart. Yes, Anil. You'll be tested for it. Yes, you need to memorize it. It's not tough. Yes, you can look at the periodic table, but in the periodic table, these things will not be written there. Yeah, period number you can write and you can identify. So all that's why I said you have to practice it a lot. You just remember that D will start from 3D, 3D, 4D, 5D, 6D. And you have to remember that this is 4F, this blank. Ready, children? So I'm going to hide this periodic table. Let me see if I have another periodic table here. Yeah, this one. And I'm making the column here, the column needed. S has 2 groups. D has, oh, this one is not, even that periods are not made. Okay, 1 second. Let me share a periodic table with you. And we are going to practice it. So this time, I'm just going to show you the periodic table the way it is there in the exam. And you are going to use this periodic table to write the electron configuration. This is the periodic table, right? Okay. So first thing in the periodic table, write down the period numbers. 1, 2, 3, 4, 5, 6, 7. Okay, children, give me the all the orbitals. You remember we did the electron configuration of OG last time. You're going to start from this one. This is, what is this? Yeah, type it here. Okay. Vivan, are you there? Yeah, but you were not responding, not answering earlier. I called your names. No, Vivan. I called your names 4, 5 times. It's a very important thing going on, okay? So don't even miss for a single second. Please ignore all your friends, all your chat messages. I'm your friend now. I'm the only one with whom you will be chatting and talking and writing and listening. Only fun friend during this time. Okay, so this is 1s2. Now for this one, start from here. Naisha, second period 2s, not 1, right? 2s2 and this one 2p6. Check for this next one. This is 3s2 and this one. So give me the complete period number configuration. Like period number 3 is 3s2 3p6. Period number 4, 4. Give the complete. What is this? What is this? What is this? 4s2 3d 10 4p6. Period number 5. 5 children. 5s2. So is it difficult to memorize, Anil? You can use the periodic table. You just understand and memorize the periodic table. What are the orbitals? Then it's very simple. Period number 6. 6s2. After 6s2, can you see this blank? And this blank is for 4f. 6s2, 4f14, 5d10, 6p6. Period number 7. 7s2, this blank. 7s2, 5f14, and then 6d10 and 7p6. Yeah. Is it okay? So now you are ready to write on electron configurations. I'm going to circle elements and you're going to give me the electron configuration. This is up to here, this one. But we are going to write it in one single line. Like I've written as 1s2 and then this. You can write it, put a comma here, like in a single line. After a shell, like 1s2, put a comma. After this shell, put another comma. Separate different shells by commas, right? These electron numbers, they will go slightly as superscript. As 2. That's the number of electrons. Ready, children? Okay, give the electron configuration of sulfur. Uh, okay, you people can give me the configuration, then I'm going to teach you one more thing. Where is 3D, Arjun? You're not looking at the periodic table, Arjun? Where is 3D? Is there any 3D? Yes, good. Good. Okay. Mhm. Okay. Vivan answered the question. Vivan? Yeah, I think yes, he answered earlier. Okay, anyone has any problem till now? Okay, good, Vivan. Thank you. So, anyone has any problem till now? No? Now, learn one more thing. It's called as noble gas notation. Noble gas notation. Like, for example, if somebody is asking you to write down the electron configuration of lead, so we have to start from 1s2. That is called as expanded notation. Start with 1s2 for the lead. Let's give the electron configuration to lead. Expanded. Expanded means you're going to show all shells. Expanded notation. Expanded notation. Yeah, first you give me expanded notation, the one which we have just learned. So what is it? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14. Is it in period number 6? Yes. 14 is fully filled, then d10, 5d10, and then 6p2. Schuyler has given it. Yes, Anil, Schuyler, good. Put commas between the shells. Nivriti, good. But every time writing such a big configuration, you know that complete chemical nature is controlled by the valence shell. Valence shell is the outermost shell. So we are learning a new word, valence shell. Valence shell is the outermost shell of the electron configuration. Outermost shell. It is the one which is reactive. It is the one which is participating in chemical nature. So this is the valence shell. So what they do that they give us noble gas notation and option where I need not to write down the inner shells. These are inner shells. Please learn the word inner shells. Inner shells. Now I'm going to highlight the inner shells of lead. These are inner shells. They don't participate. These are inner shells. I'm going to highlight the valence shell. This is the valence shell. We can avoid writing inner shells when we are talking about valence electrons and Lewis dot structures. Every time is difficult. So what they say that lead is here, right? Inner shell represents xenon. See, this one is up to this. So inner shells is xenon here. The noble gas before that element, xenon, for lead. So you start from here. Here. Put xenon in square bracket. This is inner shell, children. Inner shell. Inner shell. These words are very important. And then you come to period number 6. What is this? 6s2. Then 4f14. Then 5d10 and 6p2. And this is the one. In this, we have 6s, 4f, 5d. So which one is the outermost shell? The one with the highest principal quantum number. So what is the highest principal quantum number here? 6. So some children and the books, and it's perfectly all right. It is the right way of writing. That you put xenon, you write 4f14 first, then 5d10, and then 6s2, 6p2. This is your valence shell, outermost shell, valence shell. Yes, Nivriti. You see that here, how many electrons are here in this? 54. You count it. This is 54. And this 54 electrons has the configuration of xenon. Is it okay? Arjun, are you asking any question? Yeah, because there are some uh, anomalous energy order because of these shapes. Yeah, so xenon, this is the noble gas configuration, xenon. This one, Arjun? Now you need not to write all these things. Do I need to write all these things now? Is it easy to write every time? No. So it's a simpler way. That's the difference. There is no other difference. The only difference is it's easy for you. Okay. So children, can you give me the electron configuration of noble gas configuration of arsenic? And you're going to tell me the inner shell and the valence shell. You will write the electron configuration the way you have learned on the periodic table. I'm answering what Anil is asking. But when they start talking about the valence shell, then we can put it in the right order, only in the noble gas notations, not in the complete. Like you remember last time, I think Vivan gave us the answer in which he changed all of them according to Aufbau Principle. If you remember, Anil, then I said that, okay, no, just do it in the last shell, only in the last shell, Anil, the valence shell. Okay, there you can put them in the right order 4F, 5D, and then 6S and 6P. Oh, it was not you? Somebody else, maybe. Was it Afan? Afan, your answers? Afan, I cannot see your name. No, 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 they will not. You are answering, Afan. Okay, fine. So, ready for arsenic? Let's write down the electron configuration of arsenic. Noble gas notation, children. So, what is the noble gas before arsenic? Argon. There is no need of calculating, checking. You just check. Which noble gas is before arsenic? Argon. So, put argon first in square bracket. The noble gas before that period, like if arsenic is in period number 4, what's the noble gas after period number 3? Argon. So that will come here in square brackets. Then 4s, this is 4s, 2, this is 3d, 10, then 4p, 3. Now what is the inner shell here? Inner shell. Anil, now you just pay attention how I'm writing, okay? If you write like this, perfectly all right, you will get full marks. What is inner shell? Inner shell is argon. But what is valence shell? This is valence shell, but this is not the part of valence shell. So that is the reason they say that when you are using noble gas notation, put it in the right order. 3D first, 3D10, 4s2, 4p3. Now this is the valence shell. How many electrons are here in the valence shell? Children, how many electrons in the valence shell? 5. These are the ones which are responsible for chemical reactivity. Is there any special thing about this electron configuration? Is it fully filled, exactly half filled, or partially filled? Just pay attention to P. It's exactly half filled. If they ask you to put this in box representation, 4s, only one orbital, it has 2 electrons. 4p, 3 orbitals. How the electrons will go? One in each. one in each, with parallel spins, Hund's rule. Is it okay, children? This stable configuration, arsenic. You're understanding this now? More practice? I will release a quiz here to all of you. You know, Ariba is doing everything in very systematic manner. I'm really impressed the way she's working. And in fact, she's helping me also to get organized. If I miss some video, if I miss something, she's the first one to telling me. Anil is also working hard. So in fact, all of you are trying your best. But looking at the quiz, doing quizzes regularly, I'm not asking you to work very hard, Arjun. Arjun, you have to do the quizzes, no? So doing quizzes regularly is the most important thing. Not doing in one day that, oh, I'll do it this Sunday, all of them. No, no, I don't want that. That's not learning. If you're doing it like this, that's not a proper learning. It's like eating everything during lunch and now I'm not going to eat for 3 days. It's like that. Okay. So please have a spontaneous, regular way of learning. That learning is permanent, smooth, and slow. Slow, smooth. They always win the race. Okay. So, ready for more questions? Shall I erase this now? This time, I will ask many questions when you write on the electron configuration. I will ask inner shells. How many electrons are there in inner shells? Valence shell. Valence shell means the one with the highest principal quantum number. Write on this, children, in your notebook. Valence shell is the outermost shell with highest principal quantum number, with highest principal quantum number, right? This is PAL, quantum number, main quantum. Inner shell is argon, but you are going to include the electrons of the other shell also. Like for example, I'll give you example here. So let's start. Ready, children? You're going to give me for iodine, noble gas notation. Noble gas notation. So okay, Nivriti is there. Very good, Nivriti. Very good. Nivriti, can you tell me how many, what is the valence shell here? Valence shell. Nivriti is already giving us. Remember, this has to be square bracket, krypton, square bracket. Nivriti, by mistake, I think you typed curly bracket. 5s2, 4d10, 5p2, 5, sorry. Can I write it in the other order? This is also correct. But for our understanding, it's always better to write it like this. Can I write it like this? Yes, I can. Now, what is the valence shell? Nivriti, valence shell is this. How many electrons? No, 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 no. 5. Oh, you are saying 5 number. Okay, yes, good. How many electrons are there in valence shell? How many electrons? 7. Now, what is inner core electrons? Inner core. This is inner core. This complete. They are not participating in chemical reactivity. So how many inner core electrons, Arjun? 36 plus 10. 46. Is it okay, children? Okay. I'm going to erase this now. Ready for another question? Give the noble gas configuration of cesium. Cesium. Very easy. How many? What is the valence shell? What are the inner core electrons? Yes. Yes. Good. And valence shell is 6. 6. How many electrons are there? Valence electrons are? How many valence electrons? 1. So children, you're getting it? You're understanding this? Now I'm going to show you one thing. Let's work specifically with this period number 1. Let's write on the electron configuration of every element, starting from hydrogen. Naisha, yeah, no problem. Ask your questions in case it's not clear. So we are doing this one, the group number 1. Let's start with hydrogen. Give the electron configuration, then lithium, then sodium, and then see the similarity. And give me 1 second, children. Hydrogen is 1s1. Lithium is, give the noble gas notations. Helium 2s1. Sodium is neon 3s1, right? Noble gas notation. Naisha, don't take the shortcuts. Okay, see, I know everything, but still I'm writing. I'm not just writing outermost shell. Okay, till the time we are not expert, don't try to use any shortcuts in learning. Okay, you can use later on when you're expert. 4s1, then rubidium. Rubidium is krypton 5s1. Then your cesium is xenon 6s1, and then francium. Anything which you see here which you feel like 7s1, 7s1. Yeah. Okay, Shiler, we are on francium. Yeah. Okay, good. Now, anything, any similarity you can see here, Naisha? Naisha, you're still using shortcut, okay? Don't use them till the time you're not expert. Yes. Everything has 1 electron in the outermost shell. 1 electron. Can you see that, children? And in all of them, it is outermost shell is H subshell, S. It is S1. So can I say the general configuration of this family is NS1? Can I say? 1s1, 2s1, 3s1, 4s1, 5s1, 6s1. And how many valence electrons are there? 1. What is the group number, children? Group number 1. Group number 1 has 1 valence electron. Can you now, in your notebook, the way we have done with group number 1, can you do with group number 2? What's the configuration of beryllium in terms of noble gas configuration? Noble gas configuration, children. Helium, this beryllium, first element. Helium, 2s, 2. Arjun, square bracket is on helium, right, Arjun? The way Afan has written, see? 2s2. Now, magnesium. Now, put it in your notebook, children. Magnesium, calcium, strontium, barium, radon. Write it in your radium, sorry, not radon, radium, in your notebook. And now tell me what similarity you can see. What is the outermost shell in all of them? S2 in all of them, not 2, S2, right? So how many valence electrons are there in all of them? Yes, Naisha. What's the general configuration, children? Naisha is already talking about general configuration, thinking fast. So what's the general configuration for this complete family? Yes, good thinking, Naisha, good thinking. NS2. And this is period number 2, so 2s2. Period number 3, 3s2, 4s2, 5s2. Period number 1. Let me use some light color. 1, 2, 3, 4, 5, 6, 7, 5s2, 6s2, 7s2, like this. The general configuration is of the valence shell. Yes, Naisha, in all the groups. We are writing general configurations of the groups, not of the periods. Group. Group number 1 has NS1. Group number 2 has NS2. I'm going to block this part, this one. If I block these two things, that is, which blocks I have blocked, which two blocks I have blocked, don't say sorry, Naisha, you are learning, okay? Keep asking questions. These two DNF. So, what is there? Only S and P. So, write down, children. S block and P block. This is called as main periodic table. Main periodic table. Most of the chemistry which you are learning in AP chemistry is from here. So you will be hardly doing any D block chemistry and F block. F block you will not touch, but D block, yes, maybe you'll do some configurations, ions. We'll talk about something about D block, but not for F block. Is it okay? Main periodic table, SN. So we have to discuss the general configuration of S and P. So can you write down the configuration of this family and tell me the outermost shell? Start with boron. Noble gas notation is helium, 2s2, 2p1. Go for aluminum, go for gallium. In gallium, you will have 3D also. Is 3D? That will also be there, right? In gallium. Indium will have 4D. Thallium will have 4F, 5D. And the last element is 5F, 6D. Yes. So boron is this. Let's write down for thallium, noble gas notation, TL. The noble gas inner core is inner core, xenon. And then what is this? 6s2, 4f14, 5d, 10, 6p1. Okay, tell me what is the outermost shell? No, 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 Arjun. You can write it in the right order if you want, but you have to always identify the outermost shell. Right order, after filling the electrons, right order will be this. 4f14, 5d10, 6s2, 6p1. So outermost shell is this. The highest principal quantum number. Yes, Vivan. And the outermost shell of the boron is this. Can you see the similarity? So what's the general configuration? General configuration. Yes, Anil, very good. Ns2 and P1. Children, you have to take S with you because it's a shell. I'm talking about the valence shell, the outermost shell. The valence shell is sixth. So in that sixth shell, you have 6s and 6p. Each group has its own general configuration. Each group. You're right, Naisha. This is general configuration of boron family. How many inner core electrons are there in thallium? Inner core electrons. Inner core. This, all these, which are not the part of your valence shell. So xenon is how many electrons? Xenon? 54. 4f14. So 14 from here and 10 from here. Afan, any confusion here? Afan and Vivan? Okay, good. So these are the questions. They're on the website also. Inner core electrons, valence electrons. Okay. We are doing general configurations also. You're learning a lot right now. Very new things. Noble gas notations. So now without my help, can you work out the general configuration of the carbon family? Carbon family, children. General configuration. Okay, Anil. Arjun. Good. Shailer. Good. Good, Naisha. Good. Good, Afan. Is there anyone who is struggling with it? Good, Vivan. Is Ariba good? So now let's see. Carbon. You said, okay, let's give me the configuration of carbon, children. Noble gas configuration of carbon. Helium, square bracket, helium. Arjun, I said noble gas configuration, so you can write like this. 2s2, 2p2. Can I put it in the form of like in S subshell? Remember, there is only one orbital. In P subshell, how many? Can we put the electrons? How many electrons in the S? Two. How to place them? One up, one down. And in P subshell, I'm going to use Hund's rule now. Hund's rule. Like this. So please learn this also. They will not pair up. They are not pairing up. Yes, two electrons with parallel spins. Hund's rule. Some teachers they call it as Hund's rule. Hund's rule. I'm just using Hund's rule. These are one like this, other one like this. Means they are spinning in the same direction. They have the same spinning directions. So this is called as parallel spins. Naisha. Are we clear about it? Can you change this configuration for nitrogen? For nitrogen. Same configuration for nitrogen. So I can write nitrogen here. Helium 2s2, 2p, 3. So what's the general configuration of nitrogen family? Schuyler is already writing it. NS2, NP, 3. NS2, NP3. Now you can see that this is NS2, NP1. Carbon is NS2. Remember? NP2, carbon. And nitrogen is NS2, NP3. Oxygen will be NS2, NP4. Fluorine will be NS2, NP5. And then this noble gas configuration, what is this? This one? This one, children? What are you writing? Don't write hydrogen family. There is no hydrogen family, Arjun. You just write, it has a very specific name, noble gases. Arjun, you are wrong. It is NS2, NP6. There is no D here. We are in the P block. We are not in the D block. We are in the P block, right? Go slow. Think before you answer. Okay. So children, for the nitrogen, we have NP3. So it means one more electron. Don't you think that this is exactly half filled? This one? This is exactly half filled. Yes, it is very stable. Not most stable, more stable. Yes, more stable than partially filled. Is it okay? Less than fully and even lesser than your noble gas configurations. So now children, are you ready for the D block? After doing S and P main periodic table, we'll do the configuration of D block, right? And here you will see some anomalous configurations in this and in this. Now AP is saying that they will not test you for it, but I'm in the habit of teaching it because it's not difficult. So are you interested in learning? Maybe AP is not going to test you. Okay, good, very good, perfect. So let's start with scandium. Scandium. Give the configuration of this family. So we work with scandium in noble gas notation. So it is argon, 4s2, 3d, 1, which I can write in the right order now. After filling, they will fall back to right order. 3d1, 4s2. What is the outermost valence shell? Valence shell here, children. 4s2, right? Okay. Now, if you go for next deuterium and then this lanthanum and actinum, which are here, lanthanum, actinum. So they all are like this. So what's the general configuration? General configuration. 3D1 means N minus 1 D1 NS2. Can I write it like this? Because if it is 4, this is 3. If it is 5, this is 4. If it is 6, this is 5. Like this, right? If your S is N, D will be N minus 1. Any objection? Okay, good. So that's the general configuration of scandium family. Now, without my help, all of you are going to give me the general configuration of titanium family. Titanium. Anil, any question here? Are you comfortable with it? Okay. Titanium family. So first you write the configuration of titanium and then convert that into general configuration. Arjun, yes. Shiler, good. Nivriti, any doubts here? Okay, good. Can we keep going on now? Now you have seen the pattern. Follow the pattern. Then what is vanadium? So titanium, you said titanium family is N minus 1 D2 NS2. What is vanadium family? N minus 1 D3 NS2. What is chromium family? Chromium. And there you will see one anomalous jump. Chromium family, you are expecting N minus 1 D4 NS2. This is what you are expecting. But no. Naisha, chromium family, chromium, this one. D1, D2, D3, D4, right? So N minus 1 D4 NS2, that's the chromium family, children. You're expecting this, but it is not. Because when I make this D, if I make 5 d orbitals, make 5 d orbitals, 1, 2, 3, 4, 5, draw it in your notebook. Put these electrons, 4 here. Parallel spins, children, parallel. Naisha, you are asking this word, it has come again. And these two are with, these are paired, paired, right? Paired. Okay, check. This one is just one electron short of exactly half filled. So one of the electron will jump from here to here, like this. And then what's the configuration? It's stable. It's exactly half filled. To get the exactly half filled, you can jump only one electron. Don't expect that, okay, I can jump here also. No, no, you cannot. Because jumping of electron from one subshell to another subshell is not free. It costs you money. Money here is energy. So jumping one electron is energy wise okay. I can do that. But jumping two electrons energy wise, it will not be okay with me. I can purchase this, but I cannot purchase two such things money wise, right? You're getting the point? So what's the general configuration of chromium family? Ns2. Okay, we are going to write down n minus 1 first, but you can write it Ns2 first also. There is no harm. So n minus 1 d5 ns1. This is exactly half filled, stable, right? So all of you can give me the configuration of tungsten. Tungsten. Very popular with young children. I don't know, they have some kind of some love with the sound of the word tungsten. Write the configuration. Not the general, complete. Noble gas notation. And noble gas is waiting for the answer. n minus 1. So that's the general configuration, Vivan, you're giving me. I want normal configuration, complete configuration in noble gas notation. Am I audible, children? Okay. Yeah. Okay, Naisha, please write on for Naisha to rejoin. Tell her to rejoin. She cannot hear me. Any one of you, please. Tell Naisha to rejoin. Thank you. Thank you, Shaila. Tungsten. So you start with xenon and then what is this? 6s2 and then 4f14, then 3d, not 3d, sorry. What is it? 6s, 5d, 5d, 5. Now put it in the right way. So xenon, 4f14, 5d5, 6s2. Outermost shell is this one. So it has only 2 valence electrons, right? And it is stable because this 5d is exactly half filled. We are good with this? No, Ariba? Remember we jumped 1 electron from Ns to D to have exactly half filled. Ariba, it should be 5D 5, not 4. Oh, 6s1. Oh, children, yes, 6s1. Ariba, thank you. This is 6s1. 5D 5. Yeah, that's why she was asking me that is it 5 or 4. So children, take care. This is the valence shell, and the valence shell you can see only 1 electron. So now can you work with the copper? It also has anomalous configuration. So let's write on the configuration of copper element, and then we are going to work out the noble gas, general configuration. Copper in noble gas notation, children, argon, right? Then 4s2. Always write down the period number here so that you will not get confused with the period number. Copper is in period number 4, so 4s2. This is 4s2. And this is 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. Can you now think of something? If I jump 1 electron from here to here, don't you think that I'm getting stable, fully filled d subshell? Yes or no? Yes. So this is not the configuration. This is the configuration of copper. Because here you are getting fully filled d subshell, which you can write like this also. Argon 3d10. This 3 number first. Lesser number 4s1. So what is the valence shell here for argon? Valence shell. Or not for argon, for copper. Valence shell for copper. And how many valence electrons are there? Only one. Yes. Children, try to have stable internet connectivity. I know it's very troubling when your internet is not working properly. I cannot stop the class. I have to keep going on. So try to have some stable internet. Generally, a stable internet will make your learning better. Okay. Even if my internet is unstable, I find it very difficult to concentrate and teach. Yeah, Naisha, try to have something stable alternative also. You know, I have right now, I'm professional in teaching. I'm doing this work only. So I can understand that I should have plenty of internet connections. I do have plenty of them. But every house, I think in USA also, they have minimum two internet connectivity, two different companies. If one is not working, then you can be dependent on your other company, maybe the mobile internet, something like that, right? So now we are on the next concept, children. I know time is less, but you can do it. We'll write on the electron configuration of ions. You already know how these ions are formed. We did the nomenclature. Ions are formed by losing or gaining electrons, losing or gaining electrons. So if I say what's the configuration of sodium plus, so plus means the electron is lost or gained. This plus means how many? How many? So if I say write down the configuration of sodium plus, expanded notation. Let's go for expanded. So what is it? 1s2, 2s2, 2p6. Do we have 3s1? No, that is lost. And what is this configuration, children? This one is neon. So sodium 1 plus is nothing but the configuration of neon. It's not neon. It's just the configuration of neon. And configuration of neon is very stable. Yes, you can write, but don't think that is neon. It's not neon. It's still sodium because number of protons in sodium are 11. Number of protons in neon are 10. Identity of the element is from the protons, not from the electrons. Electrons, they keep changing during chemical reactions. So we identify elements from their atomic numbers, that is number of protons. But the electron configuration now of sodium plus is neon configuration and it is very stable. And that's why sodium always exists. You will never see sodium in nature. Arjun, if you try to search for sodium, this sodium, with no charge, you will not find it. How you are going to find it? As Na plus in abundance in all salts, NaCl, Na plus Cl minus, like this. This is in seawater, plenty of it because it's stable, right? Can we write the configuration of Cl minus, children? And let's see, is it stable? Cl minus means one electron gained, Cl minus. So it is, Cl is here, children. So how many electrons? 18. It's just argon. Yeah. You can write it like this: 1s2, 2s2, 2p6, 3s2, 3p6. It's stable. That's why you will not see even chlorine, Cl2 gas in nature. No, no. Maybe on other planets, not on Earth. It's very reactive gas. But yes, you will see plenty of compounds containing Cl minus, plenty and plenty. All most of the salts, they have Cl minus. Is it clear? I'm adding one more word here: losing or gaining electrons in valence shell, outermost shells. You will add electrons in the outermost shell. you will remove electrons from the outermost shell, right? Is it okay, children? Write it down. So ions are formed when electrons are added or removed in the valence shell, in the outermost shell. You cannot put electrons or remove electrons from the inner shell. That you are going to learn when we are going to do periodicity. I'm going to erase this. Now, based on that definition, I will be asking questions. Let's do that. Give the electron configuration of Cu plus. It means one electron is removed. So first you write down the configuration of Cu. Oh, you want to see noble gas configuration? Write the configuration of Cu, just Cu. In terms of noble gas, argon 3d10 4s1. Can I say that? You remember exceptional configuration? I'm saying copper 1 plus. Now this electron will go from where? From 3d or 4s? What is the valence shell? Valence shell is 4s. Electron will go from here. So what's the configuration of copper 1 plus? Argon 3d10. Is it okay, children? Nivriti? Okay. Nivriti, you're fine with this? Ready for more questions? Give the configuration of manganese 2 plus. So first of all, write down the configuration of manganese in noble gas notations. Manganese, argon, then how come neon? Arjun, go slow. Naisha, no. Arjun, entirely wrong. You're in period number 3. But manganese, I'm not talking, oh. Children, I'm talking about manganese, not magnesium. Manganese is here. Arjun, Naisha, manganese. Yes, Shailer, Anil. This is 4s2, period number 4. That's why I was telling you to write down the period numbers always. And D1, D2, D3, D4, D5. Yes. So can I write it like this, children? 3D5, 4s2. So what is the outermost shell? Outermost shell, 4s2. So electrons will go from the outermost shell. So what's the configuration of manganese 2 plus? Manganese 2 plus. Mm-hmm. Manganese 2 plus. Yes, Anil, very good. Argon 3d5. So that is the reason I was telling you the meaning of the valence shell. You are going to remove electrons from the outermost shell. The order with the D block is different. We are going to fill S first and then D. But after filling, they will fall in the right order. And the valence shell is the S subshell. You will remove electron from the S, not from D. Is it okay? Now, can you give me the configuration of Fe3 plus, children? Fe3 plus. This is the last configuration. And in the next class, I will give you a very small test in the class only. So come prepared and join at the right time. test on the configurations. And of course, I'm going to upload there also, but we need some more practice. After that, you are ready for quiz on the website. FE3 plus, children. Oh, is this the answer you're giving me for FE3 plus, Naisha? Okay, then work out FE3 plus. Yes, Anil. It is argon. So first you write down Fe. Fe is argon. 3d6, 4s2. 3 plus means you remove 3 electrons. So 2 will go from here and 1 will go from here. So it will be 3d5. Can you see these two electron configurations are same? Yes, Arjun. So when electron configurations are same, then Afan, these configurations which are identical, they are called as isoelectronic species. Very important concept in the AP exam. Isoelectronic species. The configurations. So what is the meaning of isoelectronic? Same configuration. Isoelectronic is written here. Species with identical. Species means ions, atoms, whatever. Species with identical electronic configuration. Identical electron configuration. EC. They have identical. You can read this word identical. Same. Very important word. I think today I told you about noble gas notation. Exactly half filled configurations are more stable than partially filled. Isoelectronic species. What else we did today? New words, new vocabulary. I'm just scrolling your chat messages. Yeah, children, do you remember any other new word we did? Of course, we did. You remember I told you main periodic table. What is main periodic table? Main periodic table. S&P. Now, before you leave the class, answer one question. All of you are going to answer. Making of this electron configuration is based on four rules. I'm not talking about quantum numbers, four rules. Is it four? No, three. It's not four, three rules. Can you tell me what are those three rules? Remember this? Pauli's exclusion principle. Second, yes, yes, Arjun. Hund's rule. Third, Arjun is already talking about it. Aufbau Principle. So when you are making the electron configuration, writing the electron configuration, you have to take care of these three rules. And then we did some exceptions here, if you remember. Chromium, copper family, they have exceptional configurations. And that was based on the fourth rule, which is different. We don't have any specific name for it. But I told you that exactly half filled and fully filled are more stable. Exactly half filled and fully filled are more stable. Take care of all these things are more stable. When you are writing the configurations, if you can make a configuration exactly half filled, like in case of this chromium, by jumping electron from one subshell to another, that can be done. Like here, one electron jumps from 4s to 3d to have exactly half filled chromium configuration. Here, one electron jumps from 4s to 3d to make it exactly fully filled d subshell, right? So we'll start from here again. Write down that we are going to do more ionic configurations. And I will be starting periodicity also. If you have any doubts, any questions, you can stay back in the class, children.